Hello everyone, today we're going to be creating a flat plate boundary layer using CCM+, and we're going to be doing that by finding the 3D velocity field of a smooth flat plate by simulating an empty wind tunnel that has the dimensions of 1 by 1 by 5 meters when the fluid flow is at 300 degrees Kelvin and it's traveling at 15 meters per second. Now we can do some preliminary analysis to figure out what sort of physics values and conditions that we're going to have to choose to set up the simulation, and we can do this using Reynolds analysis. Using the Reynolds number, we can find where the flow can become turbulent, and depending on where it becomes turbulent, it will help us choose our physics conditions. So first, you see the formula for the Reynolds number here. Reynolds number equals rho VL over mu. Now rho is fluid density, v is the fluid velocity, L is the length of the plate, and mu is the fluid dynamic viscosity. And we know that for this example, if the Reynolds number is greater than 5 times 10 to the 5th, then the flow will become turbulent. So in order to find exactly where on the plate it becomes turbulent, I just plugged in 5 times 10 to the 5th for the Reynolds number and the following values except for the length in the equation here. And having the Reynolds number set to 5 times 10 to the 5th, I found that the flow is turbulent at length equals 0.523 meters. We can go ahead and start CCM Plus to begin modeling our simulation. So first, we will need to create our wind tunnel. For that, we will need to expand geometry, right-click on parts, new shape part, and block. We know that the dimension of our block is 1 by 1 by 5, so we'll need to change one of the axes to 5 meters. And then just click OK. Now our block has been created, but we can't see it. In order to see it, we need to create a scene. So we can just click on Scenes here, right-click, New Scene, and Geometry. Now that we have our geometry scene open, we can see the block that we created. Now that it's done, we need to separate the surfaces, because right now if you check in parts and you go to block, surfaces, you'll see that this is just all one big surface, and we want different physics values for multiple surfaces. So you'll need to click on block surface and click split by patch. Here you can choose which surfaces you want to essentially separate. So we click on the front face here, and we're going to name that the inlet, and that is where the flow will be entering the wind tunnel. Create. We can click the back, and we'll call that the outlet. And then the bottom surface we'll call the plate. And we can just leave these other three surfaces alone. Now you can see our surfaces are here. And now you want to right-click on the block and assign the parts to a region. And we're going to want to create a boundary for each part surface. Apply. We can go ahead and close this. And now if we go into regions, we can see we have all of our boundaries that we created. We'll want the three sides that we left alone to be a symmetry plane, so we go to type and we set it as a symmetry plane. We want the inlet to be a velocity inlet, and we want the outlet to be a pressure outlet. The plate can just remain as a wall. Now that that's set up, we can go ahead and begin to choose our physics models. So we go to right-click on Continua, New, Physics Continuum. You can double-click on Models. Now here we'll have three-dimensional, steady, gas, coupled flow, real gas, and equilibrium air. finish it off, we know that it was turbulent at 0.523, so we'll choose the turbulent viscous regime. We'll use the K omega turbulence model, and that should be good. Now we can create our mesh by right-clicking on Continue again and hitting Mesh Continuum. And we can choose our models for the mesh by double-clicking Models. For this, I'll be using the trimmer and the prism layer mesher. And we can go ahead and go to the reference values to give it a base size. So each of the cells will sort of follow this guide based on the base size you give it. 0.025 meters should be good for this. Once we have our inputs for the mesh, we can go and run the mesh. So this will generate our volume mesh. Now you can see the mesh has been created, and once again we can't see it on this scene. That's because we need to create a new one. So we can go down to Scenes, right click on it again, New Scene, and this time we'll hit Mesh. Now you can see the mesh. Now depending on the type of simulations that you need to run, your meshes can be finer or more coarse when you need it. And now that our physics models have been chosen, we can go ahead to the regions and the boundaries, and we can add the values that we want the boundaries to represent. So here we can go to regions again, click on the region we created, boundaries, and the first boundary we'll input some values in is the block inlet. We want the physics value for the block inlet to be 15 meters per second because it is a velocity inlet. So 15 meters per second. Now for the outlet, we want our physics value, we want the pressure value to be 0 ambient pressure. So that is 0 gauge pressure. We can see here, it's by default 0, and this is based on a reference value, and by default the reference value for pressure is atmospheric pressure. So the outlet will be at atmospheric pressure. We can also see that our static temperature is at 300 degrees Kelvin by default. So if you had a different temperature flow, this is where you would need to input your values. Now that everything is set up, we can go ahead and initialize the simulation by clicking the green flag and then hitting Run. Once you hit Run, the screen called Residuals will pop up. Once the lines are somewhat stable, you can go back to your solution and view it because it has reached a steady state. One thing I noticed here is the solution stopped iterating after 1,000 iterations, and you can see that although that some of these lines have seemed to converge and are oscillating around some constants, the TKE, the light blue line, has not. In order to extend the maximum number of iterations that the simulation will take, we need to click on Stopping Criteria and go to Maximum Steps, and we can extend it with the maximum steps input. I'll just put 2,000 for now and monitor the residuals to see when the TKA will converge. We can go ahead and just click Run again for it to continue iterating. Now you can see that the blue line has leveled out along with all of the others, and we can go ahead and stop iterating by clicking the red button up here. Since our solution has reached a steady state, we can now go ahead and view it. For that, we'll need to create a new scene, and this time we're going to create a vector scene. You can see that there's not much visible on our wind tunnel yet. That's because we need to go to regions and we need to drag the region onto the solution. Add it to vector 1. Now you see the solution. This is a side vector view of the wind tunnel, and you can see the boundary layer growing on the bottom here. The red arrows represent fluid moving at roughly 15 meters per second, and the green, yellow, orange you can see on this gradient here represent different velocities. And that completes our tutorial on how to create a flat plate boundary layer by simulating a wind tunnel using StarCCM. Thank you for watching.